Enthalpy change of neutralisation. So the enthalpy of neutralisation is the energy change that accompanies the neutralisation of aqueous acid. So we remember that all acids contain H+, by an aqueous base. Now, bases that are soluble in water all contain hydroxide ions. And the definition says to give 1 mole of water. So that's quite important, water liquid. Okay, so this is the enthalpy change that we're trying to measure. So it's an acid-base reaction. And we're going to revise how you determine an enthalpy change. So to determine an enthalpy change, then what you're going to need to do is you're going to need to do a polystyrene cup in a beaker for insulation and support with a lid and a thermometer. So you're going to have a lid on your beaker. This is going to be a thermometer. And we're going to put this as a beaker. We've got a polystyrene cup, which gives us good insulation. We've got a lid, better insulation, and then we've got our chemicals inside. So we're going to put one of our two, and it doesn't really matter which we start with. So we're going to add a known volume and concentration of acid to a polystyrene cup and record its temperature every minute for 3 minutes. That allows us to get a line of best fit through those points. At the 4th minute, add a known volume and concentration of the other reactant, which in this case is alkali. And stir. You don't record the temperature at that point. Record a further 5 to 10 temperatures. Every minute so that we get enough to get a line of best fit. Extrapolate and find the temperature rise at the 4th minute. And this takes account of heat loss. So you end up with a graph where you have your time on the bottom and your temperature up the side, and you get a few points before addition. And you can draw a line and extrapolate it out. And then, remembering that at the 4th minute we added our chemical, then we'll get a few points after, and they will be cooling down to the surroundings, and we can draw a line of best fit through those as well. And at 4th minute, we can draw a vertical line to work out delta T. Then we can use Q equals mc delta T to get the Q in joules, and then delta H is Q in kilojoules divided by, and because this is enthalpy of solution, the moles of water. So we're going to divide by the moles of water here. So let's have a look at an example. So we're going to start with 50 centimetres cubed of 2 mole per decimetre cube sulfuric acid, neutralised by 50 centimetres cubed of 2 mole per decimetre cubed calcium hydroxide, and the temperature rose from 21 to 48.5. So we can see that delta T is 27.5 when we subtract one from the other. So remembering that C is 4.18 joules per gram per Kelvin, I mean, they'll tell you that in the exam, we can do Q equals mc delta T. Now, what's the M? The M is what the thermometer is measuring, and so it's the mass of the solution, and this solution was 50 add 50, 50 of each. So we want 100 times 4.18 times 27.5. You type that on your calculator. Get this number. which we'll need to convert to kilojoules in order to use it in the delta H calculation. It says calculate the number of moles of water formed. So the first thing we need to do is calculate the number of moles of the acid. Moles are very clever. 50 centimeters cubed, 2 mole per decimeter cubed. So that's 0.1. And then if we look at the moles of the calcium hydroxide, that is also 50 centimeters cubed of 2 molar. That is also 0.1. And if we look at our balanced equation, we've got H2SO4 and calcium hydroxide, and they're in the same proportions, which is great because neither is limiting or excess, so we don't have to worry about that. But if we look, we can see that there are 2 moles of water for every mole of either one of these. So the moles of water is going to be 2 times 0.1. I can use either because they're both the same moles and neither is limiting, and so I can pick one or the other, but it's going to be 0.2. So if I want to calculate delta H, remember I need Q in kilojoules over moles of water. So I'm going to take my 11,495 and convert it to kilojoules, and then I'm going to divide by my moles of water, and I'm going to get the answer 57.3 kilojoules per mole of water. But the temperature rose, so I insert a minus sign to say that it was exothermic. And so my answer is minus 57.3. We've got a second example, so we're going to write our balanced equation first. H2SO4 plus NaOH is going to give us Na2SO4 and H2O. So if we balance that, we're going to need a 2 here. And a 2 in front of the water. Okay, so we could work out the moles of each of these things and work out which one we're going to use to get the moles of water. So I've got 0.05 moles of sulfuric acid, and I've got 50 times 10 to the minus 3 times 1, 0.05 moles of sodium hydroxide. But the ratio is 1 to 2. And so to use 0.05 moles of H2SO4, you need 0.05 times 2, because the ratio is 1 to 2, moles of NaOH, i.e. 0.1. Haven't got 0.1. 0.1 is greater than 0.05, so the moles of NaOH are limiting, haven't got enough to use it all, haven't got enough to use up all the sulfuric acid. So use moles of NaOH. You always lose the limiting reagent because that's the maximum you can use to find moles of water. So moles of water equals, because the ratio of water to NaOH is 2 to 2. So moles of water equals moles of NaOH, and the moles of NaOH that we actually have is 0.05 moles. So that's what I'm going to use in my Q equals MC delta T calculation when I get to the delta H is Q over moles part. So again, I'm doing 50 add 50. So for my Q, I've got 100 times 4.18, and my temperature didn't rise quite so much this time. My delta T is only the difference between 25.75, looks like I was using a thermometer with quite good resolution, 6.75. And that's coming out as 2,821.5 joules. Okay. Now, delta H we said is Q in kilojoules over moles of water. So that is Q into kilojoules, so divide by 1,000 or times 10 to the minus 3. Remember that the moles of water, we use the limiting reagent to help us find that out. And so this is coming to 56.4 kilojoules per mole. And remember, we have to put the minus sign in because the temperature rose. We can see that that answer is very similar to the last one we got, because an acid and an alkali, it's the same ionic equation. What about different acids? So then this is what we're looking at. The enthalpy change of neutralization of sodium hydroxide with different strong acids is the same. So let's highlight that. Doesn't matter, as long as they are as long as they're a strong acid, it's the same value. Why is that? So all strong acids fully dissociate. Okay. They all have the same ionic equation with OH minus ions. So it's H plus. So they all fully dissociate to give H plus. They all have the same ionic equation with hydroxide ions. So since the reaction is the same, delta H is the same. Okay, so we can just highlight that as well. The question then asks, the enthalpy change of neutralization with a weak acid is less exothermic than with the strong acids. So why is that? Weak acids only partially dissociate. Most of the acid is undissociated. Okay. So our HX is in equilibrium with H plus and X minus. Therefore, energy is needed to break bonds, cause dissociation, which makes the process less exothermic. And I just want to draw a little diagram to help us understand that. Run out of space here though, and squeeze it in. So if we imagine for our strong acids, we've got H plus and OH minus, and we said in both those examples it was roughly minus 56 to get us down to water liquid. When we're a weak acid, the first thing that we have to do is put energy in to make our HX dissociate. What that means is our minus, our delta H, is less negative than the strong acid, because the first thing we have to do is put energy in to cause dissociation before energy can be released on neutralization. And so our delta H is the difference between the energy in and the energy out, and so it is less negative.